Okay, today we talk about sensors, and we start with some definition of the main quantities that are of interest for defining a sensor and for describing its property. So let's start from a definition. A sensor is a device that receives a stimulus and responds with a signal. In this is a very broad definition. It's so broad that it does not tell us anything specific about the sensor, but is a good starting point for us. So what is a stimulus? The stimulus is the quantity that we want to measure. A quantity or a condition that we want to measure, because we want to measure, we could be in a situation in which we want to measure if a person is in a room or not. Of course, that is not a quantity; is a situation, a condition that we want to measure, that we measure. And then the signal, in most of our case, is an electric signal. This is not strictly required for the definition of a sensor, but of course, since we're dealing with electronics and electrical quantities, for us this is going to be an electrical signal. Which means that the physical embodiment of the signal will be a voltage or a current or a charge. Okay, in the case of electrical signal, this is the choice that we have. Another important aspect that we need to highlight is the fact that typically with a signal comes an energy. So the signal response is associated to some energy that is transferred with the signal. So just to draw a very generic diagram, if this is the sensor and this is the system which is connected to the sensor, we have from the sensor to the system typically some information flow, which is the information content of the signal, plus some energy, which is of course associated to the signal, because if we want to embody the signal in a voltage, of course, with this voltage, some energy will be transferred. So we have a flow of information which is connected to a flow of energy from the sensor to the system. And where does this energy come from? Okay, of course, this energy can be extracted directly by the sensor from the environment, or can be provided by the system. So sometime, not always, we can have, let me use a different color just to indicate that it is optional. While the first two arrows are always there, we can have a transfer of energy from the system to the sensor, because we need to supply some energy to the sensor in order to have it work, make it work. Okay, let me this is optional. Depends on the type of sensor and on the type of measurement that we want to do. Okay. Now, for the moment, we are dealing with some definitions. Some of the words that I will use are words that you have already heard, and then you just need to, let's say, put them in a framework, in a more well-defined, in a better defined framework. Some other words are new for you. A word which is strictly connected with the sensor is the transducer. Okay? Let me just put the transducer in relationship with the sensor. Okay. Since most of us are Italian, of course the Italian translation for these two words is sensore for sensor and trasduttore for transducer. Okay, let me write this one because it's not obvious. I don't know if all of you have already heard this word. Okay, what is a transducer? A transducer is let us call again a device. A device is a very small system which has a function. Okay, so also device is a very generic word, but it is a device which transforms the information from one form of energy to another. Okay, device. Let's use the same wording. So I need to stress this definition because, as you can see, it is somewhat correlated to the definition of a sensor. So the sensor provides a signal in response to a stimulus, and the transducer transforms information from one form of energy to another. For example, what is a transducer? The membrane of a microphone is a transducer because it actually translates some information in the forms of sound waves, which is in the form of sound waves, into information which is in the form of an electrical signal at the terminals of the membrane, or if we go at a lower level, in a distortion of the membrane. Okay, so the same information is translated from acoustic waves to the formation of the membrane, and since, for example, the membrane is piezoelectric, this deformation of the membrane is translated into an electric voltage at the terminals of the membrane. What is the difference with respect to a sensor? Typically, the difference is that the transducer is part of a sensor. Because the electric signal which is produced by a sensor is already in a form which can be transmitted to the system. Okay? So here we have to put a different sign, and typically we have a situation like this. This is the stimulus, for example, in the example that I made before, the sound wave. Then we can have a first transducer, so transducer 1. Then we can have a second transducer which transforms the information from the second form of energy to a third form of energy. And then we have some let's say electronics for signal conditioning. Let's say and the transmission. And then we have the final signal in a form which can be received by the system. And the sensor is the total system consisting of all the transducers plus all the electronics which is required for conditioning the signal and for transmitting it. For example, if the signal that we want at the output is a digital signal, then the electronics for signal conditioning typically must be connected with the second transducer, which transforms the information into an electrical signal. Then this electronics must amplify the signal, must filter it, then it must transform the signal into a digital signal with an analog to digital converter, and then finally it must transmit it using an appropriate protocol. Okay, these four functions have to be performed by the final electronics block. Okay, let me just filtering, amplification, AD conversion, analog to digital conversion, and then transmission. Here we can have one transducer or more than one transducer. Of course, the first transducer must have as an input the stimulus in the energy form of the original quantity that we want to measure. The last transducer must have at the output the information in an electrical form. But can be an electrical, for example, in the case of the microphone that I mentioned before, we typically have just one transducer, which is an piezoelectric membrane, which transforms the sound waves into an electrical signal which is analog to the sound wave. Analog means which has the same type of time behavior. But this electrical signal, of course, cannot be connected to this USB port of the computer. Of course, inside we have filtering, amplification, analog to digital conversion, and also typically a USB interface in order to transmit the signal to the USB port. And this is the whole, so this, the microphone, is a whole sensor. Okay. Another word that I need to introduce is the concept of actuator. The concept of actuator is, of course, related to the concept of the sensor. Actually, we can say that the actuator is the inverse of a sensor, okay? Because it essentially transforms an electric signal So if I want to write the same expression, I can, instead of transforms, I can write receives as input, and so receives as input an electric signal, and provides a stimulus at the output. So essentially the opposite, the inverse of the sensor. Typically the stimulus is embodied in a different form of energy. For example, by keeping the example that I made before, of course the inverse of a microphone can be a loudspeaker. Loudspeaker receives as input an electric signal, and of course it is transformed in sound waves, which is the final stimulus. Also, in this case, the actuator works like this. This is the signal. Then we have some electronics as the first stage, electronics for signal conditioning. And then we have one or more transducers in order to provide the stimulus at the output. Of course, in terms of blocks, the actuator is very similar to the sensor, but the similarity ends there because the type of transducers are of course very different, and also the type of electronics is very different depending on the application. But when one works on sensors, one typically also works on transducers, and type of skills for designing electronics for sensors and electronics for transducers, let's say, are somewhat, not totally, but somewhat overlapping. Okay, now with sensors and actuators, we can start to talk about data acquisition systems. So let us consider the main building blocks that we have. We have on this side an electronic system, which is partly analog and partly digital, and let's assume that this is the world. Okay, the world that we want to measure, the object that we want to measure. Okay, and we can have different types of sensors. We can have sensors which are in contact with the system that we want to measure. When I say world, I mean the system that we want to measure. It can be, it can really depend on the type of application. And these are contact sensors. Plus we can have some sensors which are not in contact, that we call remote. The numbers are totally let's say arbitrary, and just drawing an example of a situation that we might have. Now, at the output of these sensors, we have an interface. At the output, we have an electric signal, as we know, and then we have an interface to the electronic system. Sometimes the signal is already conditioned to not require an interface. Sometimes we require a specific additional interface. The interface simply is needed to adjust the protocols, for example, the levels of voltage of the digital signal that we have as an output to the sensor and required as an input of the electronic system. For example, we can have some of these sensors can be passive, some can be active. If we have, if this 4 is an active sensor, we have some actuation circuit which simply provides the energy to activate the sensor. Okay, in this direction. Okay. Or we can have let's say instead of a sensor, here we can have an actuator, which of course is activated by the electronic system. Okay, and on this side we need to use, for example, a multiplexer in order to select only one sensor at a time for the microcontroller. We can have, if the signal are analog, we can have as an optional let me use the blue for the optional. An analog to digital converter, if this is optional, if the signals are analog. Okay, if the signals are digital, of course this is not required. And then we have a microcontroller which receives these signals as input and provides as output the electric signals for the actuation circuits, and of course talks with the memory and some peripheral circuits. Okay, so if we have a system which is controlled by microcontroller, and the system needs to have sensors and actuators, of course this is the more general structure that we might have. Of course, the microcontroller must have some inputs and some outputs. The signal, in order to be sent to the input of the microcontroller, must be properly conditioned. So this means that, of course, the sensor sends an electric signal, then we will have an interface in order to get the data into the electronic system, and then we typically do not have too many I/O ports for the microcontroller, and therefore we need to use a multiplexer to select one input from a sensor at a time. Again, this actuation circuit and this actuation circuit has to transform the signal coming from the microcontroller into some energy to activate the sensor, or if this input signal from the microcontroller goes to an actuator, of course internally the actuator will have the electronic circuits required to transform the signal into the proper form of energy to execute the actuation. In the example that I often do of a smartphone, we can have very many type of sensors. We can have, of course, the display. We can have the accelerometer. We can have the gyroscope. We have temperature sensors and so on. And of course, they are the signals from those sensors are sent to the microcontroller in this way. And on the other hand, we also have some actuators, because, for example, the display is an active sensor that must receive energy in order to work, as well as the accelerometer. There are also active sensors. The camera is also an active sensor. The temperature sensor somewhat often is not active, but sometimes it is. I mean, most of the sensors require some sort of energy to work. But of course we have also other actuators, such as, for example, the loudspeaker or the vibration circuit, which are directly driven by an actuator. So this is a very generic description of the system. Let me just stress the fact that this is an active sensor because requires energy, and 1, 2, and 3 are passive sensors because they do not require additional energy to work. This line that I've drawn here which separates the electronic system from the rest, is called also signal conditioning interface. It's called signal conditioning because in order for the signals to enter the electronic system, they must be properly conditioned, which means they must have the voltage levels, the current levels, and the frequency behavior required to be sent to the electronic system, to be received also by the electronic system. Okay. Let's get into some details related to the sensors, some sort of terms for the classification of sensors before we look at the properties. Okay, there are many parameters that allow us to classify a sensor. One of them is something I already mentioned, is this passive or active sensor. So the passive sensor does not require external energy to operate. The active sensing requires external energy for the sensing operation. Then another classic type of classification is in terms of absolute sensors and relative sensors. So the absolute sensors provide a measurement with respect to an absolute scale. And of course, the relative sensors provide a measurement with respect to a relative condition. Okay, so measurement with respect to an absolute scale. This is a measurement with respect to the relative condition. We can make many examples of this situation. For example, the gyroscope in a telephone tells me the orientation of the phone with respect to a given relative condition, which has been fixed at the time of the set of the gyroscope. So I only know how many degrees the phone has rotated with respect to the initial condition. Sometimes, for example, temperature sensors already provide me the temperature in absolute degrees. So with respect to an absolute condition. Okay, there are many of these examples. They are pretty easy to make. And of course, the last thing that I want to enter here in terms of classification, which is actually the most common, which defines typically the name of the sensor, is in terms of the conversion phenomenon, which means the quantity that we want to measure and the type of transduction that we make. how we transduce one physical quantity into another physical quantity. Of course, different types of mechanisms, not only different types of quantities that we want to measure, but different types of mechanisms that allow us to convert the information from one physical form to another physical form. Okay. Even if the starting and final form are the same, but the type of conversion can be different. Okay, we shall see some example. I suggest now to make a break, and then we continue on this topic. Just a 10-minute break, and then we continue.